So in this video, we're going to use this concept of the standard electrode potentials to figure out voltages that you would have if you hooked up two particular half cells. All right. So let's start with this question right here. What would happen if you had a magnesium half cell and you connected it up to a voltaic half cell with a voltaic cell arrangement, which of course would mean we're going to hook in a voltmeter so we can figure out the voltage. It would not only tell us the voltage, not only tells us the force, it also tells us the direction that the electrons would be flowing. We would also need to have a salt bridge. Some of these things, just realize that they have to be there. But the important thing is just going to be comparing the identity of these things. All right, so how are we going to do this? Step number one, write down the more positive of the half reactions, or of the reduction half reactions. All right, so what we're going to do, we want to find the one that involves magnesium and the one that involves silver. All right, so let's go back over here to our standard electrode potential, and remember, all of these are written as reductions. All right, so the only ones that would occur as written with the hydrogen electrode are the ones that are positive. So let's find the one that's more positive. So here's the silver one, and the other one was magnesium. That's over here. So between the two of these, it is the silver, which is the more positive between them. All right. So keep in mind, when I say more positive, it does not have to be positive. All right. If we were comparing two things, say magnesium and zinc, they're both negative, but the one that is more positive would be the zinc, because negative 0.76 is more positive than negative 2.37. All right, so this is the reaction right here that would actually occur. All right, so what we would do is we would write down that reduction, and we can write it as a standard reduction potential, and you just write that value. Second thing that you're going to do is you're going to write the more negative one in its opposite direction. All right, because if the more positive one is going to be undergoing a reduction, the thing that it's operating with is going to be undergoing the oxidation. So going back to this table, we said that this is the one that is the more negative. All right, so we want to write this reaction, but it going in the opposite direction. So magnesium going to the ion plus the electrons. All right, so again, so this is the way that one would occur. All right, and if you were wanting to make sure that your half reactions balanced out, you might notice one thing, which is that this first reaction only involves one electron and the second one involves two. So you could double it so that things would cancel out, and when you combine these, you would get your overall reaction. But one thing I want to point out, when you double this reaction so that you can write the balanced reaction, it does not double the voltage. All right, it still would have this potential, relative potential compared to that hydrogen electrode. All right, so here's the big thing to remember: the EMF, the electromotive force of the cell, is nothing but the electromotive force of the reduction plus the electromotive force of the oxidation. All right. Well, so since this is now written as the oxidation, all we have to do is sum up these two values, or sum up these two values right here, and we can figure out the electromotive force of the cell. All right, and that's going to be 3.17, and that's actually a very large voltage, and hopefully that should make sense, because you're going between things that are really far apart on the scale. All right, the closer two things are, the smaller the voltage, the farther things are apart, the higher the voltage. All right. One other thing that I want to point out about our answer is that if you've done this so that you're writing the actual reduction reaction that will occur and the actual oxidation, you should always end up with a positive number. All right, and what the positive number indicates is that it's a reaction that would actually occur. If you end up calculating a negative one, what it indicates is that the electrons would be flowing in the opposite direction. All right. So, in fact, if you wanted this to register as a negative 3.17 with your voltmeter, all you'd have to do is when you set up your little reaction between the two, just take this wire. Right here, plug it into the other side of the voltmeter, take this wire right here, plug it into the other side right there, and what that would essentially do is just reverse the flow of the electrons through your voltmeter, and it would just register it as the opposite sign. It would go from positive to negative. All right, but since the electron flow is still the same speed, amount of force, the value is the same. It's just its direction would change. All right, so the second problem, just give you a little bit more practice. Let's say that we're doing it, and I'm going to write it with a little shorthand. What if we had a 1/2 cell that had lead metal and lead nitrate as your dissolved solute, and in 1/2 cell you had zinc and zinc chloride as your dissolved ions. All right. Well, first of all, let's figure something out. All right. Well, when we look at this ionic compound, what's the ion here? All right, that would be lead +2. All right, and taking a look at this ionic compound, this, when it's dissolved, is going to make zinc +2. And so what we want to do is we want to find the reduction reaction in that list that involves lead going to lead +2, and we want to find zinc going to zinc +2. All right, so where are these? Okay, well, here's the lead +2 going to lead metal. All right, so this one's going to be one that we're going to use. And we're also going to use, what did I say, zinc? Yes, zinc. So zinc is right here. Okay, so again, the first thing that we want to do is to find the more positive. All right, so between these two, it's the lead one, which is the more positive. All right, so even though it's a negative number, remember, it's negative because compared to the hydrogen electrode, that describes the direction of the electron movement. But now, since we're interested in electron movement between these two things, the negative means doesn't have its same meaning. All right, so this is the more positive, and so this is the reaction that would occur as written. Since the zinc is the more negative, what we want to do is take this reaction and turn it around. All right, so that's what we're going to do. We're going to write that lead one as a reduction. And since we're going to take that zinc one and we're going to turn it around and write it as the oxidation. And remember, when you do that, you take the value that you had here and you write it as a positive number. And that's to indicate that if you do this in reverse, this is now the voltage that you would have as an oxidation. All right. So again, the same concept. The overall electromotive force of the cell is the sum of these two things. All right, so we're going to add these two things up, and that gives us positive 0.63 volts. Okay, and again, it should be positive if you have written these half reactions in the direction that they would actually occur in this voltaic cell. All right, so for this particular total reaction, that's what you'd have. And hopefully this makes sense. If you calculate the voltage, it's 0.63, and if you look between these two things, that should be essentially the difference between them, and that's the way these will always work out. So I'm going to assign you guys a couple of practice problems with this, and hopefully you'll be able to accomplish that.